So yesterday we discussed the coupling of gauge vectors, gauge fields, to gravity, and that is the action. Actually, that's the one action, and indeed we can add terms as long as they transform correctly. And an example of terms that you can add is given precisely by what you obtain by replacing the field strength, which is this combination, by this other combination, which contains an additional term. So if you replace f mu nu with this, it's like taking this action and adding certain terms that transform correctly. That you can do. That's a non-trivial difference only when this, which is the torsion, is non-vanishing. So let's check that the torsion transforms correctly. And we start from the transformation of gamma, of the Christoffel symbols. How can you work it out? Well, we know in general the transformation of a connection. You just have to apply this formula with the right omega, small omega and capital omega. So small omega is what? Instead of omega AB, you will go to this gamma mu nu, which is gamma mu rho nu dx rho. And then, as far as the change of basis is concerned, you check what this omega should be. So instead of EA you have the forms dx mu. So here you have to check what the change of basis will be by working out that omega. Well, we start from the Jacobian. The Jacobian is, well, now we derive omega, capital omega, we'll insert it inside and then we get the result. So, yes, certainly we can write dx mu prime, that is equal to partial x mu prime, partial x nu dx nu, and so you have omega. That is the Jacobian of the transformation. We also need omega minus 1, let's say nu rho. It's the matrix that gives the identity when you multiply it by omega, so it's obviously partial x nu, partial x rho prime. So we now use this formula. Omega prime, small omega prime, will be omega mu nu rho prime dx rho prime. That is omega prime. And that will be equal to those things. So let's, now that we know what capital omega is, let's continue to call it omega, capital omega, without replacing. We will do it later when it will be necessary. So for the moment, that is just omega mu alpha gamma alpha beta delta dx delta, and then there is omega minus 1 beta nu. Okay. Plus omega mu alpha d omega minus 1 alpha nu. The last, actually here we can, this is a differential, so let me write it like a partial derivative times the differential of the basis dx rho, because we want now to isolate dx rho. Here, however, we have dx rho prime, so you have to put what? Dx rho prime is omega times dx. Omega, so that is an omega sigma rho dx rho. So now you have an identity where you, if we drop dx rho everywhere, because this is a one form, so the coefficients should be the same, we have omega sigma rho gamma sigma nu prime, there is a mu here, equals, and then you copy that. This delta is rho. Rho beta, omega minus 1 beta nu, plus omega mu alpha partial rho omega minus 1 alpha nu. And so it's sufficient to multiply by omega to the minus 1 to move this matrix to the right hand side and write this. And what you get there is that gamma alpha rho beta transforms in the first contribution here as it should. So the superscript gets multiplied by omega, and both subscripts get multiplied by omega to the minus 1, because you have for beta you have beta nu, and for the other you have rho sigma. Because if I multiply by omega minus 1, that is what gets rid of the matrix that appears on the left hand side. Okay, but there is an additional part which will be what you obtain by copying this: omega mu alpha, omega minus 1 rho sigma, partial rho omega minus 1 alpha nu. So if gamma were a tensor, it would transform just with the first piece. There is a second piece, but the second piece doesn't depend on gamma, and so in the difference it disappears. Basically, this is the idea, but let's check. So let's check the transformation of the torsion, namely the difference between this and itself when you exchange those two indices. So we want the transformation of this difference. And now we just have to take this formula and copy it. So gamma mu prime sigma nu minus gamma mu prime nu sigma. So you just have to take this as anti-symmetrizing sigma nu. When you observe that when you exchange in this first piece sigma nu, it's like exchanging rho and beta, and so you just have here inside the difference between gamma alpha rho beta and gamma alpha beta rho, which is the torsion itself. So this piece goes into what you want, which is the tensor that you want. So that will be gamma alpha rho beta minus gamma alpha beta rho, and then you have omega minus 1 rho sigma omega minus 1 beta nu. Instead, what we want to do is to show that the rest goes away when we anti-symmetrize. So let's copy the rest of mu alpha omega minus 1 rho sigma partial rho omega minus 1 what was it, beta nu, alpha nu in this case, minus the same thing when you exchange sigma nu, rho nu partial rho omega minus 1 alpha sigma nu. Now the last piece here is indeed 0. Why? Well, first we have to observe one thing. Let's focus on this derivative, because with a partial integration, so-called, we can move it here, because you see this is a partial rho, and there is an omega minus 1 with a contraction alpha with omega. Omega minus 1 is 1, and so you can move this d rho there with a minus sign. But the same thing here, because here also it's contracted alpha alpha, so you can in both cases move partial rho on that. And what you remain with is something simpler. And symmetric now. Anti-symmetric, because now this is anti-symmetric in sigma nu, so it is also anti-symmetric in rho and alpha. If you exchange rho with alpha, you have minus 1. But this is symmetric. Anti-symmetric, and this is symmetric. If you exchange rho with alpha, and this is the only place where we use the definition of omega mu alpha. What was omega mu alpha? Here it is. It's partial with the index of the lower, with the lower index of x mu prime. So this thing is equal to partial rho partial alpha x mu prime, which is symmetric in the exchange of rho and alpha. So that disappears, and the torsion transforms correctly. So at the end you have just this. So this is an exercise to show you that we can use the formulas we have used we have found are so generally that they can use everywhere, literally. Now, among the other terms that you can build with for the action of the gauge fields, there is one that can be built with differential forms. This one also is a differential form. Now we will go back to that point in a moment. As we said yesterday, when you define this integral, which is an integral on the manifold has to be split into various contributions. In each of them, you can use appropriate coordinates, but normally you cannot use the same coordinates everywhere, because sometimes they become singular and singularities. It's better to make a change of coordinates in the overlap between two charts and then move with the new coordinates. So strictly speaking, from the point of view of mathematicians, this is not really a nice way to express this, because it's an integral on the manifold, and it's the integrand is instead not something intrinsic, written in a way that's intrinsic of the manifold. So there is a way, mathematically speaking, to build a 4 form, because this is a 4 form in general, but it's absolutely useless. It's just ad hoc to do the same. So we will continue with this way of writing without burdening the notation for nothing. But there are situations where instead they are, physically speaking, less interesting, where you can write a term that's manifestly the integral of a form, so intrinsically invariant. For example, you can consider this thing. The integral of m of f wedge f. No indices, no coordinates. This is just the integral of a differential form. F mu nu is a differential. F is a differential form. Then when you make this explicit in coordinates, then what you have is F mu nu F rho sigma 1 over 4 dx mu dx nu dx rho dx sigma. This is a wedge of 4 differentials, and that is something you can replace with in the common notation. The tensor epsilon mu nu rho sigma, which is such that epsilon 0, 1, 2, 3 is equal to 1, and it is completely anti-symmetric, apart from that, times d for x. So that object becomes 1 over 4 integral on m of f mu nu f rho sigma epsilon mu nu rho sigma d for x. That's in classical electrodynamics, that is E scalar b or h, while the integral of f mu nu is E squared minus h squared. So this is a topological invariant. You can show that it is the integral of a total derivative, so-called. This is easy to prove, because if you replace f mu nu with what it is, that's 1 over 4 integral on m d mu a nu d rho a sigma epsilon mu nu rho sigma d for x. But you can also write it that way. So it's the integral of a divergence or maybe you can write it that way, the integral of a divergence of something, which means that it can be, by Stokes' theorem, it can be transformed into the integral on the boundary of the manifold. We do not need to do this here, we can do it directly there, at this level. So let's do it. You have this object, which you can write like that, but you can also write it like that, because D is nilpotent. And so by the Stokes theorem, that becomes the integral on the boundary of something. Now, this doesn't affect the field equations, the equations of motion. It might have some interest in some specific cases when you have a manifold with a boundary, but we will meet terms like these in gravity also. They are around. That's just to show you that most of the times what you can write down in a clean form, mathematical form, by means of integrands that are already built very easily with the forms you have, is not physically very interesting. And what you can, for physics, what's interesting for physics instead is an action. We will continue to write like this, although you will find Hodge-star dualization of forms to write this as a more intrinsic volume form. It, in the end, will not make you gain anything. So here we will continue with the more physical approach. Everything we have said for electromagnetism can be generalized to non-abelian Yang-Mills theories. We just mentioned this without details because you will probably see in other courses. Non-abelian gauge theories, which are called Yang-Mills theories. They can be coupled the same way. There, the difference is that instead of having F mu, you have indices which we will denote by AB with a dot to differentiate them from the flat space indices, which is built with many connections because they have this extra index. And then you have a correction here which involves certain constants that are called structure constants. And this gauge theory is associated with some gauge group G, for example, SUN. And then these indices A dot are in some representation, which is called adjoint representation of that gauge group. And so this is a connection that is, if you want, it's like omega AB. It's a connection with two indices, but the difference is that here you have or gamma mu nu. In the case of gravity, both indices are the same type. Here they are different types. So you will have transformation rules for those and covariant derivatives for those indices as well. But the correction here is much simpler than here because it's just a product. Oh, by the way, this is anti-symmetric in this. So it's always a form. You can always embed it into a form, a differential form, because it's anti-symmetric. And however, this is a product, so it transforms correctly under the transformations. Every formula we have written before can be written in this case. For example, you can build an action like this. Okay. So this is just to say that if you meet non-abelian gauge theories, they are embedding in gravity, their coupling to gravity is basically straightforward. The two types of indices here doesn't talk to each other. They do not conflict in any way. So there is and this action, as well as every term you have to write, is not only invariant under changes of coordinates, but also invariant under certain transformations that are those of the gauge group G. And by the way, the transformations of that type will be of the same form we have already met. We'll just write the formula with U belonging to the group, and this is reminiscent of our formula because it's always the formula for the transformation of a connection. So you will have certain extra space and an extra transformation, but it will always be at the same time. And two types of indices will not conflict with each other, so it's not a big deal to do that when you need it. You can forget it for the purposes of this course. But non-abelian Yang-Mills instead is important, so that you will have to know about. Actually, in the case of the abelian case, we can also check what this is. Abelian case means electrodynamics. Electrodynamics is associated with the gauge group U1. U1 means phases, which means that these objects U are phases, but they depend on the point. And so if you want to apply this formula for the transformation, you will get the usual gauge transformation. A prime equal to U A U minus 1 plus U D U minus 1 will be e to the I lambda A e to the minus I lambda plus e to the I lambda du minus 1 minus I lambda. And so this is A minus I d lambda. And the reason why there is this I is that in this notation I'm using a basis of anti-Hermitian gauge fields. Okay, it's this A is in this formula. This A is I times the usual A. So in some most of the books actually will find formulas with slightly different, because normally I use a basis for non-abelian gauge fields where the representations are multiplied by I. They are made of anti-Hermitian matrices instead of Hermitian matrices, so there is an I somewhere. But normally, so when you make all definitions as usual, you will have a gauge transformation of this form, this gauge transformation. And of course, the gauge transformation of F is as the gauge transformation of the curvature so connection. And so this is just like the transformation of R. Okay, this is just to mention these things, but it's not really what we deal with in this course. It's just to tell you that it is not a big deal to embed non-abelian gauge theories in gravity when you know what to do with the abelian one, with electrodynamics. Now instead we have to go to the fermions, which is a little bit more tricky. So that we will treat with some care, and because it's what the field-buying is all about, you cannot couple the fermions to gravity through the metric tensor. You need the field-buying, and you need to consider what we have already called local Lorentz transformations. So first we start from flat space and recall how to treat fermions in flat space, which you might have seen with, or you might see in other courses, but we need to recall it because then we have to generalize these formulas. So a fermion can be written as a pair of doublets and what do you need to study fermions? Well, Pauli matrices, for example, and Dirac matrices. Let's start from the Pauli one. So we add the identity, which we'll call sigma 0, and then the Pauli matrices, properly called sigma 1, sigma 2, and sigma 3. we build a sort of vector by means of those. And that we write also as sigma 0, sigma vector. Sigma vector is the triplet sigma 1, sigma 2, sigma 3. Then we define sigma tilde mu equal to sigma 0 minus sigma. And the property of the sigma tilde is that they can be obtained as follows. You take sigma mu, you calculate the complex conjugate, and you multiply it by sigma 2 to the left and the right. You can check this, because sigma 2 is it's purely imaginary, where the other matrices are real in the spaces. So in the spaces, you have this. Then you can define the gamma matrices. As follows. Which satisfy the Dirac algebra eta mu. Okay, a property that we need to stress and we use is that gamma 0 is equal to what? 0, sigma 0 is 1, 1, 0. 0, 1, 1, 0. So gamma 0 squared is equal to 1. Now, Lorentz transformations. Lorentz transformations are changes of coordinates such that eta mu is equal to, is invariant, basically. And so you have this. So you know that x prime squared, which is x prime mu eta mu nu x prime nu, is equal to x squared, which is x mu eta mu nu x nu. Why? Because if you replace it, you will have lambda mu rho x rho eta mu nu lambda mu sigma x sigma, and then you use that identity to say that this is equal to eta rho sigma. And so x prime squared is invariant. if I raise an index here, so eta mu nu, let's say eta mu alpha, that's delta mu alpha, and that I can write as, by copying, eta rho sigma lambda sigma nu eta nu alpha. That I can also write as lambda rho mu, and I can view this as the same lambda with indices. This index is lowered and it becomes rho, and that other index nu is raised, so becomes alpha. So it's the inverse, so-called. Yes, the inverse, because this is the inverse. The product is 1, is a matrix with indices like that. And observe that the contraction is in the first two, so there is a transpose as well. If this holds, of course, you can, as we used earlier, the inverse is unique, so you can also multiply the two in the other way, and you will still have the identity. What is the other way? That means that instead of contracting these two, you contract the other two. So let me say that this is this and rho and rho. And that will be equal to delta nu mu. Now, okay, the fermions. How do they transform under Lorentz transformations? The fermions will transform with a certain matrix that we have to determine, and we have to associate a matrix A with the matrix lambda. So given a Lorentz transformation, which is determined by a certain lambda, what is the matrix A that performs the transformation of the fermions? Let's determine it. Since we are splitting fermions into doublets, it's better to split also A, and A will have this form, two blocks, diagonal blocks and zeros, and the two blocks are still to be determined. And let's see what properties we want. As you know very well, it's important to introduce psi bar, which is psi dagger gamma 0. And what is the transformation of psi bar? That is the transformation of psi prime dagger. So you take the dagger of that. Times gamma 0. But that is also psi bar gamma 0, A dagger gamma 0. Because gamma 0 squared is 1, so psi bar gamma 0 is psi dagger. So if we want, you know that the mass term is invariant. So if we want this to be invariant, let's see what we need to require. Psi bar psi, that should be equal to psi bar psi. So we should have this equal 1, or psi 0 A dagger gamma 0 A dagger gamma 0 equal A to the minus 1. So this is one thing we want. Then we want that the Dirac action be invariant, which means psi bar prime gamma mu partial mu prime psi prime, that should be equal to psi bar gamma mu partial mu psi. Notice that the gamma matrices are not changed. They are numbers, and they should be invariant. The gamma matrices, as delta mu nu is invariant under rotations, they should be invariant under the transformation. We will see how that happens. So that is equal to what? Psi bar prime is what we have. Psi bar prime can be written as psi bar. Yes. Using this formula, psi bar prime is just psi bar a minus 1. Because a minus 1 is that. So this is a minus 1. Then we have gamma mu d mu prime, that is partial x nu partial x nu partial x mu prime, and then you have psi prime, that is a psi. This Jacobian is something we met already. So in the transformation, yes, we have met it already in general, but we have to work it out in this particular case. So let's do it. How to do it? We know that these are the transformations. So that is it. That means that partial x mu prime partial x mu is equal to lambda nu. And so partial x nu partial x mu prime will be the matrix that contracted with that gives the identity, and that will be the inverse. And the inverse will be, as you know, as we said before, first it's a lambda. It should have one index here and one index there instead of that. And what is the index up? It's nu, and the index down is mu. So to rewrite this, we have psi bar prime gamma mu d mu prime partial mu prime psi prime. That is equal to what? Psi bar a to the minus 1 gamma mu. Then there is this lambda mu nu partial nu. Let me write a outside of the partial sign because we are now in the global case. So these are global transformations, they are constant, and that should be equal to psi bar gamma nu partial nu psi, which means that this object should be equal to gamma. By the way, this is precisely the statement that the gamma matrices are invariant. Because remember that the gamma matrices have spinorial indices and an index mu. So when you make a Lorentz transformation, the index mu gets a lambda, and the spinorial indices gets an A. So you transform all the indices of gamma, you do nothing. That's why they are invariant. This is the meaning of this identity. So we have to find a transformation that leaves the gamma invariant. Given lambda, we have to find A such that this is true. So let's suspend 10 minutes.